Good morning. I'd like to introduce our next speaker, who is Peter Canty from ADI. He is an applications manager for industrial Ethernet. He's worked with ADI for more than 30 years on technologies including power management, wireless receiver technology, and mostly taking up the challenges of introducing single-pair Ethernet technology to the industry. I'm going to turn this over to you.
Thanks very much. So good morning, everyone. So what I'm going to do this morning is talk a little bit about cable diagnostics in the context of 10-base T1L. So I think a number of you here understand the real value of 10-base T1L and its ability to supply high-speed Ethernet over long distances, which is fantastic and a real enabler technology for a number of industries that you can see on board behind us, for instance, whether that's process control, factory automation, building, rail communication. But it does represent a challenge then in terms of making those networks continue to work reliably. That's what I'm going to talk a little bit about today. So just by way of an agenda, what is 10-base T1L? So it's a particular form of the SPE or single pair Ethernet technology that we've been discussing here this morning. I'll then talk a little bit about cable diagnostics motivation, and hopefully that's clear that in the long distance scenario, you need an accurate, reliable method of checking results. I'll talk a bit about the diagnostic features that exist on the PHY technology that ADI actually provides today. Then I'll dive a little deeper into our TDR technology, or time domain reflectometer technology. I'll show a little bit of how we actually present that with our GUI, and then I'll wrap up and have questions. So what is 10-base T1L? So I think most of you will be familiar with standard Ethernet, if you like, where you've got 4 pairs of wires in the cable, you've got an RJ45 connector. And that's been a technology that's been around for decades. And obviously we live with it and use it every day in our lives in the office. It is a fabulous technology, but it is not a technology that's built for harsh environments. And as the digitalization of factories and buildings, etc., emerges, we need a higher speed technology. Ethernet is an obvious choice from a protocol perspective, but how do you make it more robust? And how that's been achieved over the last couple of years is through this single pair Ethernet technology. So if you see the cable in the bottom half of the diagram here, you can see first thing, obviously, is that it's just one twisted pair, as distinct from the 4 above. The barrel indicates the distance, so it can support a kilometer of cable or more, and it can provide 10 megabits of data reliably over that 1 kilometer of cable. So maybe not hugely fast compared to gigabit speeds in a typical IT network, but order of magnitude faster than you have in an OT network that supports things like RS-45 or Force 20 million. So the table then on the right-hand side just kind of distinguishes between the two. So they talked about the 2 to 4 pair. You're talking about 100 meters in a standard Ethernet environment versus up to 1 kilometer or indeed further than 1 kilometer for a 10-base T1L. Speed is 10 megabits. One of the key enablers is the 2-pin connector. So from both a complexity of installation and a reliability point of view, a single pair connector is a huge benefit to the industry. It makes the connections much more robust and much easier to install. And then an attribute of 10-base T1L that doesn't really exist with standard Ethernet is the ability to use it in explosive or dangerous environments. So particularly in process control, which was kind of where this technology emerged in terms of its need, you can reliably use your 10 megabits of data in environments that are hazardous, explosive. The energy within the cable, the SPE cable, is such that it won't be the generator of a spark and is therefore an intrinsically safe solution. And like standard Ethernet, you can actually have power over the same pair of wires. So what's the motivation in doing this, right? It's basically to take the network that you have on the left, which is kind of a more traditional network today, where you've got point-to-point connections with your device, whether that's 4 to 20 milliamp or RS-485, connected back to gateways, then back to immersion cabinets, and then doing translation between that and Ethernet, all of which kind of constrains the data that you're producing from these instruments within their environment. So what we're trying to do here is to liberate the data, as in from the IT to the edge, have it all as Ethernet. It's all Ethernet protocol. So then you can, from an instrument, not only get the reading from that instrument, you can also get when it was installed, what type of instrument it was, when is it used for calibration, when have faults occurred in it. Masses more amount of data that in a factory management, from a factory management perspective, is hugely useful in maintaining the uptime of the factory. And just a reference to the 2.4 volt and 1 volt, that is how the explosive environment technology is achieved, where the lower voltage, the lower energy can be used in hazardous environments. You're also removing gateways here now, so you're not doing any data translation. It is literally Ethernet all the way from the cloud to the edge here. So from an SPE perspective, the capability delivered by SPE to be able to provide data over a kilometer of data, that is a fantastic enabler if you think about a factory environment and the length of cables that need to be used in that environment. But these are also harsh environments. These are areas where the cable are exposed to potential dangers, whether it's AMRs crashing into them, or they're exposed to environmental conditions, or just general wear and tear. That's a lot of cable to try and figure out where there is a fault actually existing on it, right? So that's kind of the motivation then in terms of providing the capability to accurately, reliably define the type of fault and where that fault exists. If you can imagine from a maintenance perspective, the cost of being able to accurately go to the location where a fault has occurred and change it has big implications for uptime versus downtime, and therefore the cost of staying. So you've got things like junction boxes within that 1 meter, 1,000 meters of cable. Those are potentials for discontinuity with connectors misaligned or wearing out or whatever. So those are potential issues. You have non-compliant cables. So if you're trying to retrofit this technology into a building where cables already exist, those cables may not be to the standard that's specified by IEEE in terms of supporting the 10 megabits of data over the 1 kilometer of distance. But they will support some amount of high-speed data. So you want to be able to determine how far you can get with a non-compliant cable. Anything that's exposed to the outside world has a risk of deteriorating over time. So you can have connector issues that suffer from liquid contamination or shorts from the shielding braid touching the data lines, all of which can reduce, let's say, the integrity of the data. And you need to be able to accurately find out where that issue has occurred. So this is a list of all of the diagnostic features that exist on the PHY, MACPHY, and switch that we in ADI provide to the market today. So you've got a lot of the common ones like PMA test modes to determine link status, etc. You've got link quality monitoring, so MSE, which is essentially SNR, so signal to noise quality. We've got loopback modes so that you can isolate our device from the cable and determine that that's not the issue. And you've got frame generator and frame detection or frame checker, which allows you to test the link without having to provide data from another data source. And then the last one then is time domain reflectometry. So the others are very good at telling you there's an issue, but not so much about where that issue is. And that's what TDR does. So you can see in the bottom right, you're basically talking about, if you're familiar with telephony systems in the past, you send a pulse down the cable, that pulse is reflected or some form of that pulse is reflected. The time it takes to come back gives you the distance, that inflection, and the shape of the pulse can actually determine the fault timing. So what we provide then is a combination of hardware and software to actually enable this capability. On the hardware side, we've got a very accurate TDR engine, as we call it, inside the device that can accurately measure the data, can accurately convert and synthesize the shape of the pulse that comes back. So in hardware, we provide you with the raw data to actually do this calculation. Offline to that, we have an algorithm and software that actually interprets that data and provides you with the information. So again, accurately define where the fault occurred and define whether it's a short or an. So in order, not just about accuracy, it's also about reliability. You don't want to have false positives in a factory with a cable that's a kilometer long that you're going to the wrong place, the wrong location. So attributes that you have to have in that whole TDR setup are things like accuracy, as we mentioned. So defining to within a meter, let's say, of where the fault is occurring, and to be able to do that repeatedly. So you don't want false positives, false negatives. You want to be sure that that fault actually exists. You have to have effectiveness. It has to be able to operate in noisy environments and, in process control or in welding environments. There is a lot of noise being injected into the cable. You still need to be able to accurately define where that fault is occurring, even in such an environment. And you don't want false fault detections. You want this to be real data because the cost of interfering with the cable at any given point is substantial. So you want the ROI, if you like, in that point. And false positives are a killer in that scenario. So these are the attributes from a performance perspective of the TDR solution that we have today. So we certainly get you greater than 1 kilometer in distance. In fact, it could be 1,400 meters or even more. And across these different cable lengths, we have somewhere between 1% and 2% of accuracy to the location. We've got cal routines in order to remove any anomalies in the environment. So we've got offset calibration that will remove, let's say, the distance between our chip and the connector, and you're only measuring the connector the cable from that point on. And we have a calibration then around essentially the speed of light. How fast does the data move through the cable? Because there are slight differences for different cable types. So we can calibrate that out. So again, the time for the data to come back is accurate. So then some real data about the accuracy of our system. We've basically got a column of opens on the left-hand side and shorts on the right-hand side. You can see the different cable lengths that we've tested this with. And you can see then the delta between the actual cable length and what our device measures. And you can see that, in most cases, it's actually 1% or so, 1%. For the longer cable of 1,400 meters, it's 2%. So still pretty good. So what do we actually provide you with, right? So we talked a bit about the hardware that's built into the chip. From a software perspective, we provide you a number of functions. One is the basic fault detector to actually do the calculation. But then in order to enhance the accuracy, we've got calibration routines around offset and cable calibration. And then to use this, you simply call the fault detector function, and it will return the open, the short, and the distance tubes. So this is how we actually present it to you when we give you an evaluation kit if you're looking to actually assess this technology. And it just visually kind of describes what you can get from each of the routines that I just talked about. So you see the box in the middle, start, that's your fault detector algorithm. But you can see above that, you have these calibration routines that you can zero out the offset and also the MVP or the nominal velocity of propagation. And that's available from us today for you to actually download. So that's kind of it in terms of an exposure to the technology. It's a fantastic technology that enables incredible advances in terms of the digitalization of the factory. The cable lengths are really a game changer, and the data rate is really a game changer. But because of that length, it does present challenges in terms of actually identifying faults as and when they occur. So ADI does provide a solution that allows you to do exactly that. And because we have this technology, it's something that we're very happy to work with customers and partners in terms of characterizing the cables that we talked about that may be non-compliant, or discussing challenges that certain cable types may present. And it is obviously something that we're happy to engage with partners. So that's basically it. That's what I have. So any questions, please feel free. Is the interpretation that they was the big one? We do have, so we actually have a white paper that's online that actually talks about some of the cables we've looked at. So some of that data is available, yes. And then on a case by case basis, we would actually engage with partners to actually find out that data individually. Some of what we've looked at is available online, yes.
Anyone else? Yeah, I'm going to be posting the presentation spot underneath the meeting written then. And in moving live, you can go down the accountability funds.
All right. Okay. Thank you very much for your time.